I apologise for that. And given the time I've been here at this university, even I go to lecture theatres I've never even heard of before. So it'll be an experience. So we'll all try to get to the same place at the same time, and hopefully it works. The only stable thing in the whole thing is that we'll always meet in this lecture theatre on Tuesdays at this time. Everything else is quite interesting. Remembering, of course, this week is week 2. All right? So that will be on the Blackboard site. Right, let's carry on. Let's do something better. What? Push quite down to a dull moan. Let's start. This is the first lecture I gave a week ago. Was really just a sort of hand-wavy type thing, saying this is what the robots are, this is where we find them, this is what the challenges are, etc. So what I want to do this afternoon is we start to talk about the kinematics. This is how we describe a robot, describe its structure, and therefore we can start to work out the control algorithms if we want to go that far. And this will form the first part of your assignment, which I'll get issued shortly, but the submission date is going to be sometime toward the end of the month. So, that worked. So let's just refresh our memories, and if we can remember that back that far. Robot definitions. Not terribly important at this stage, but it's good to have a good grounding in them. Is, as I said, the industrial robot, the standard thing that you see on a shop floor, is defined by that statement there. But as we mentioned, that's perhaps not broad enough or wide enough to cover recent developments. So we actually made it a little bit better. And this is the one we'll stick with. An intelligent robot is a machine able to extract information from its environment, that's its sensors, and use that knowledge to move in the world safely in a meaningful, purposeful manner. In other words, it has a task to do. So we'll stick with that definition, and that will become quite apparent as we go through the various systems. I do make a slight sort of, it's rather more sort of semantics and concept-wise. We tend to split robotics up into 2 broad groups. The conventional robotics is the stuff that's on the shop floor now, the stuff that's welding your car together, etc. And we can also have this behaviour-based robots, and that's the latter part of the module where we will talk about some very interesting swarm robotics and how we can put different systems together to give us a robotic system that will work in different environments. So really, even though kinematics applies to both those groups, it really is how we identify and look at conventional robots, is what I want to talk about this afternoon. So, we're going to look at 3 and 6 jointed robots. Why we go from 3 to 6 is something that will become clear in a second. These are used for sort of the conventional industrial applications, welding, spray painting, etc. And what we've got to look at is their configuration, how we put them together, how we actually get them to do the job we want them to do. Kinematics is how we describe that, and also that will give us a brief to control. So it's that sort of remit I want to look at. So let's just consider So it's in robotic say a manipulator, device used to manipulate tools, materials without direct contact. The direct contact's put in there because in the larger case we use things like end effectors or sensing systems to sort of take it one stage further, and we don't want to worry about that at this present stage, but we're looking at sort of robot structure there. So we've got some base, we've got something which goes round, and we go down at the top. So it really consists, as you can see, of a number of segments. We'll briefly call them links, but don't call them links in practice. So we have bits of metal put together, we have a joint between them, and by moving those joints we can actually get the robot to the right place. It's as simple as that. And we have two types of joints. We can have a sliding or prismatic joint and a rotary joint. So that's all we're going to do. We're going to glue together some links, we're going to glue together some joints, and that will give us some robots. Just before we go down to some definitions. Technically, the robot's configuration is the complete specification of the location of every point on the manipulator. Sometimes quite loosely we tend to also say that the configuration is how we put the joints and links together, but that is the real fundamental definition of configuration. So we know what each length each bar is, whatever we'll call it in a second. So the configuration can be represented by a set of joint variables. And we say that that's Q1 through to Qn. And this will come back when we're talking about workspace a bit later on, so you'll get a refresher later on. If you have an object in free space, so let's assume a balloon floating in free space, that'll have a number of degrees of freedom. In free space we'll have 6 degrees of freedom. And that is the minimum number of parameters we need to actually define where that object is in three-dimensional space. Just taking a stage further, we can say that 3 of those are positioning, i.e. X, Y, and Z. Imagine our balloon, then our balloon to rotate. And how it rotates, again, is going to be a function of the axes and reference frames we actually looking for that particular problem. So we do have configurations, we have degrees of freedom, and if we have a manipulator which has more than 6 degrees of freedom, they're not terribly common, but they are there, we have a kinematically redundant manipulator. Now, when we're looking at some examples of robots which actually consist of 2 arms, you could argue, well, that's got 6 degrees of freedom, that's got 6 degrees of freedom, so the whole robot has 12 degrees of freedom. It's not truly kinematically redundant because you satisfy the kinematics of both arms. So it's a little bit more complicated than just stating that very simple statement. But if you have more than 6 degrees of freedom, you will have a kinematically redundant manipulator. And what do those look like? They actually look like that, or that's one example. So you can see a large number of each of the robots got 4 wheels. It's a pipe inspecting robot, so that thing will slide down inside the pipe. Those wheels will drive that robot down the pipe, and it has multiple joints. We need the multiple joint because we don't have the flexibility to go around bends and pipe work. However, it's almost impossible to analyse. So what we do, we lead it by its nose. That's how we program. And make the assumption that each of the segments behind it will actually follow the first segment. So the first segment goes up, all the other ones go up until past perhaps a joint, etc. So there's special applications, oil pipelines, reactors, etc. Nice and interesting control problem, but it's not it's not a terribly challenging control problem because it makes it far simpler. But as I said, we control it by its nose, we pull it by its nose through the system. So if we look now at a conventional static, so it's not a mobile platform, industrial robot. This is what we'll actually have in the first instance. We'll have a mechanical arm, and we'll have the end of arm tool. In other words, the end effector, vision system, whatever we want to put. And that will operate on the environment, or in the environment. If we now move back through the robot, we'll have a suite of sensors. Now those sensors there are not the sensors that operate in the environment, either the vision systems, the tactile sensors, smell sensors, etc. These are the sensors within the joints, which we won't look at in any detail in this module. These are your rotary sensors, your linear sensors, your optical coders that tells the control system that's where that joint is at. That's all fed into a processor, and we have a network of the program which tells the processor where to drive the robot. We have some power supplies and some drives, and we have an input device, and that's going to be your laptop or a special purpose keyboard that the robot manufacturer supplies. So that is really what goes under the, that's if you went out and brought yourself a robot, that comes in the post to you. You have all those bits and pieces. So what we really want to look at is the mechanical arm, the first point of this model. And that mechanical arm is the robotic structure. Now, as you can imagine, we're putting together sets of links and sets of joints. We have an infinite number of robot configurations. We don't do that. We go by some rules, and those rules will give us a good set of robots. We divide a robot into two parts, just for the sake of control and also for the sake of actually controllability and weight restrictions, etc. So the main manipulator, that's a free jointed, that's the big bit of the robot, it's a free jointed measure which will point the thing in the right direction. And then we've got the wrist, so it's very much using anthropomorphic terminology. We say we have a wrist, we have a robot shoulder, we have an elbow, and we have a waist. So we're using that sort of anthropomorphic signage to point you in the right direction. So really what you're concerned about at the present time is everything, if you look at the human, up to the wrist. So the manipulator will position the end effector, then the wrist will orientate. The important thing to remember is everything must occur within the workspace. This actually, if you think about it, this is blindly obvious. If you've got a robot, it has a maximum reach. So it's going to do a task, like spray paint an object, or do something else. That robot's workspace, in other words, where it can reach, the task it's doing is within that workspace. And we'll actually formally define what workspace is a bit later on, but I just want to make that statement. Depending on the robot's configuration, I work with the joint, we will change the shape of the workspace. And you'll see that when we actually work through some of these. We can then add two additional caveats to that. We can firstly say that the workspace is reachable. So that, if you put, imagine you've got your tip of your finger, I can reach anywhere in space at the tip of my finger. So that's the maximum extent. But I can't do anything, apart from point. I can't do anything with the tip of my finger. So I have another workspace, which is my dexterous workspace, and that's the workspace in which I can position everything 6 degrees and 3 degrees. So when you're designing your robot system, i.e. interfacing with conveyor belts and other sort of production equipment, you really have to have those within the dexterous workspace. Why am I worried about the reachable workspace? Anybody got any views on why I'm interested in the reachable workspace?
You don't want to quite accidentally hit the wall.
I'm worried about safety, effectively. Because effectively, anywhere within the reachable workspace, the robot can actually hit an object. So that's what I want to do, is ensure that the reachable workspace is clear of things that I don't want the robot to interfere with, and that includes humans. Because humans are fairly soft, so a large industrial robot capable of handling 20 to 30 kilograms is quite a dangerous beast when it comes up to a human being, and we have to worry about that later on, even though people have actually got around it by various different techniques. So, this workspace I keep talking about is limited. We look at the formal mathematical definition when we actually get that far into the module. But really, what you've got to imagine at the present time is the working volume is limited by three things and three things alone. What joint we have? A rotary joint will have a different path to a prismatic joint. The limits to the joint's motion of travel. So we have that. How far can the joint? Can the joint go from 0 to 90 degrees? 0 to 180 degrees? Minus 180 degrees, plus 180 degrees. Or if you're very lucky, you may get one which goes continuously, but that's very rare. And also the length of those links, i.e. the bits of whatever that keep your links apart. So your joints apart.
Sorry.
So we can just sort of say the joints are the prismatic ones are P, and the manipulator is a kinematic chain formed by links connected by joints. In each joint, you have a variable. In a rotary one, it is alpha. Start here. In a rotary one, it is theta. And a linear one, it is D. And at the bottom, you've got what they are. The important thing to remember is that don't argue with that statement. Rotary is theta, linear is D. The reason I say that is when we get to the kinematic definitions, we'll introduce two more variables, A and alpha, which look even stranger. But that then refers back to all the standard texts and all the standard matrices. So by convention, the joint variable is theta, the joint variable is D. So, just to recap very quickly on this one. Structure of the robot system, number of joints and links. We need 6 joints to give us full control. So if you sit down and say you've got 2 types of joints, you've got infinite different types of links, you can have a fairly robust discussion on how you put all these together. Don't worry about it. People are looking at this for 40 odd years and say the best way of doing it is 5 configurations. 5 configurations will satisfy all industrial applications. If you want something a little bit more special, you can actually get something a little more special. But these are the ones, these 5 configurations are the ones that you will buy off the shelf. And what I want to do is just run through these in some, not in some detail, but looking at them in detail. Right, the first one is what we call polar configuration. It's rotary prismatic. So it's this sort of beast. So you're a linear extending arm capable of being rotated around the horizontal and vertical axis. Alright, so it will rotate and then come in and out. So what sort of application is that useful for? So this is the type of robot that we use, particularly when you're dealing with hot materials and boundaries, etc. That's removing things in presses, because it can go in and out very quickly. And you'll find as you go through this that linear motions generated by linear actuators are quicker than linear motions generated by rotary actuators in general. So this is the type of thing that you'll go and you'll pick your steel out of the press, put the next sheet of steel into the press. So it's that sort of motion you want. It's also very useful if you want to go for a fairly small opening, which you may find on the foundry, etc. So that's the polar. That's good. And the workspace is that volume there. It does, remember, of course, this is only a diagrammatic representation, so you may get a little bit more in, a little less, a little bit more rotary motion, depending on the limits that you put in the system. This is called a cylindrical configuration, rotary with two prismatic joints. So you have two extending arm which goes up and down a central column, and that column rotates. Right? So it goes up and down and rotates like that. So this is a very good type of robot if you've got some parts carousel, and you're just picking parts of a very small carousel. General assembly is not terribly flexible, but it comes with the classification of being very cheap and cheap. Lots of initial robots were done like this because you could actually quite do the mathematics of it. So that is that particular design. Now, the gantry robot is just 3 prismatic joints. That is even simpler than this. So if you want to move it to an XYZ corner, those XYZ corners directly map onto your joint position. So you don't have to do any difficult transformations. You don't have to do any difficult discussion, etc., of how you actually will transform them. Remember, of course, the gantry robot can be mounted 2 ways, or actually can be mounted 3 ways. You could have it on the floor, so it goes to the floor, which is that diagonal there, or more commonly, you have it like this. In other words, you hang it from the ceiling. You need a fairly strong ceiling, but you hang it from the ceiling. And the advantage of that is, why hang it from the ceiling? So you have this space. Yeah. This is, you've got your whole floor space. So if you want to stack, this is the type of ropes used for stacking pallets, etc. So in many cases you actually find it also turns from 90 degrees, so it goes up and down. But in that sort of configuration, you don't worry about floor space. You've got, it's far more effective as space for unit movers, whatever you're going to use as a metric. It's very simple, and it's also very powerful. Those joints, those linear joints can be made very large. So if you look at a very large crane or a production line, they're effectively XYZ gantry robots. This is the one which come back and we'll look at time and time again. This is the jointed arm. The jointed arm configuration is, to a certain extent, you could argue that it is actually slightly strange. It's not very effective because, for reasons I'll show you later on, it has a very odd shaped like this diagram here, working on, because that working volume actually also exists in 3 dimensions. So it comes out as a toroid. But this was the first real industrial robot design. And the reason is it maps to ourselves. It is an anthropomorphic design. So joint 1 is your waist, joint 2 is your shoulder, joint 3 is your elbow. And you'll find that running all the way through this type of robotics. You'll have configurations which say the elbow is down, the elbow is up, the wrist is flip or non-flip. So you have that sort of thought that you must always bear in mind. That design is the Puma. Puma was the first robot of its type of this sort of size. And the first one stood rather like that off the top of the bench. Why that direction then? Sort of replicated the human. So the first robot for a real production now was not something like a gadget robot, but really would suit the attributes of the human and put them on the robot. And then you've got that sort of configuration. The final one is the SCARA configuration. This is the selected compliance assembly robotic arm. And again, it has 2 rotor joints, it has a third one which is prismatic. So you get this, if you actually sketch it out, you have this very funny shape. It looks totally useless. Except if you put printed circuit boards or something similar in that big bulge at the end, you have got a robot that can assemble printed circuit boards very quickly. Because you've got rotary ones will give you the speed, the linear one will give you the positional accuracy. And so you pick something up, spin it around quickly, drop it into place, spin it around, drop it. So this is the type of thing we use on production line. And many years ago, IBM had a whole family of these just designed to actually assemble their computer processor boards. So it's a very powerful design. This is before you actually had sort of surface mounted devices. But even now, the surface mounted devices, we have robots which have similar attributes, or we use a straightforward mechanical robot. So if you look around the industrial sector, those are the main robot configurations that you can buy off the shelf. That does not mean that you can't have any other configuration, but those may be custom built or built out of kits and parts. With the exception of the SCAR, we don't tend to put an extra end effector on it. But on all the other ones, we will put extra end effectors and an extra 3 sets of joints. And that is your wrist. So the wrist is no more than 3 joints in a very compact package. Mount at the end of the arm. So by this time, the amount of weight you've got to move, or at least the torque you've got to apply, will be reduced. So you actually have a fairly small, compact device. And this is one example. You have a number of other examples around, but this is the sort of standard Puma type wrist. You notice that the joints, if you're unlucky, can all become parallel. I will explain what happens when that occurs. And the real important point to note is that plate there, which says tool interface, which has 8 holes, and that's where you bolt your end effector to actually do the actual job. So that takes that a stage further. For reasons lost in the annals of time, we will call those roll, pitch and yaw. And that's how we define those angles. How we define the roll, pitch and yaw against which axes is something which we'll discuss later on. So that is a fairly standard bit of kit. So you'll get your main robot, you'll put your wrist on it, then you'll put your end effectors. So we'll talk about the end effectors at a later date. So once we've got that, what can we do with it? So most of these robots will do anything you actually want them, but there's some special constraints that you've got to bear in mind. As I said, rotary motion is normally quicker than the equivalent linear motion. However, if you've got to move two joints together to give you a linear motion, you have to coordinate that move. So if you're going to move that robot from that bottom of that arrow to the top of the arrow, you'll end up having to move at least two joints at a different speed and follow a path. So you've got a motion path planning problem which needs looking at. And other point to remember is that not all robots require 6 axes. We made that observation, we're just going down a foundry, may not need even 3 more axes. This one is paint spraying. Many robots, this is one of the most widely used applications robots after welding, is spraying paint. It's either paint or powder, because it is a messy, very poorly ventilated type exercise. So you've got people dressed up in quite large protective suits. So let's get a robot to spray. And also, because a robot doesn't get tired, spray painting at 9 o'clock in the morning is the same spray painting at 9 o'clock at night. It'll just keep doing it, as long as the program. We don't need a roll axis on that, so all paint spray robots have 5 axes. So it's no use, because that's coming out of cone, it's no use having that sort of final degree of freedom. So that is the basic how we put a robot together, which is quite actually easy to understand. Now, what we're now going to do is take it a stage further. And I'll get now, it's all right saying that we've got a robot or a manipulator. What we want to take a stage further forward, and we want to be able to describe it in mathematics. Well, the question you ask is, why do I want to describe this robot as a mathematical entity? Because we can analyse it. We can work about it, we can optimise its performance. So what we've done over, since some of the original papers written about, well, we'll talk about 50, 60 years ago, we've come up with a unified way of describing a robot or a kinematic chain, and therefore everything, when everybody talks about the matrix, everybody knows what that matrix is. So, robot kinematics is not terribly difficult to understand as long as you can actually think straight. So as I said, it requires a unified approach. And we've got to make some decisions on definitions, etc., which we need to think about. The first thing you must note is the most vital thing around is the right hand. Everything is referenced now against a right-handed Cartesian frame. So, X, Y, and Z, that's the positive rotation. Thumb goes down the axis, that shows you where the positive rotation is. It's as simple as that. So how do we know that a robot consists of joints and links. So the first thing we've got to do is define a joint and define a link in this sort of standard terminology. Right. This is why I said, don't worry about the symbols. The symbols are fixed, not open part of it. So a link holds 2 joints apart. So you have joint 1, joint 2, between them you have a link. To make life easier, sometimes you will think this makes it more difficult, but it really does make it easier. The axis of the joints is always along the z-axis of the originating frame. Alright, we'll take that and then we'll look at the diagram in a second, so you'll become a step pattern. That is unique across the whole robot. So anywhere where you have a joint, you have a z-axis which runs through that joint. That's the important bit. Once you get that, everything else is simple. The link axis is also along the x-axis of the originating frame. So you've got x, y, and z, which we just had previously. Joint along the z, link along the y. So x, nothing along the y. You've got to say y without y. The y-axis is there because you've got to have a y-axis. Therefore, there is two dimensions which will apply to a link. You have the normal displacement, which affects the length of your link, and the twist angle, because one joint may in fact point in a different direction to another joint. So you have just two variables. Now don't worry. This is a mathematical concept, this link. It can have a length of 0. And in any case, it does have a length of 0. Don't worry about that. Because it means that the two joints are coaxial. Or orthogonal. So, if you have a link of 0, it is all right. That's why you don't call bits of steel on a robot which goes from that motor to that motor a link. That's a structural element. So just remember that. You have structural elements in the real world, you have links and joints in the kinematic world. So that's right. So here we are. We've got joint 1. The red line is not terribly, but it should be clear enough. So that's running along the z-axis. And for each tooth we have a link, length A, running along an x-axis. That is where, if there's no rotation, up there is where the next joint will appear. And we have an angle alpha between that axis and where the joint actually goes. Right-handed frame, from down the axis, shows you which direction you're going to rotate. You're following so far? Nobody commented that following, you're all quite happy with that. So that's it. Of the direction of rotation. I can slightly better draw it in that sort of fashion there. Now, there's lots of problems which we can get into of what the value of alpha is. So we've got this thing here, Z1, X1, Y1, that's the direction, moving on there. Then we twist that frame there, Z1, X1, and Y1, we give us this one here, and that requires, as you can see, 270 degrees. Depending on which textbook you read, somebody will call that minus 90 degrees. Don't, just call it 270. So everything is positive. So that's how you get from one joint down there to the next joint there. So it is quite easy to follow. Well, at least I think it's easy to follow. Right, so that's the link. That's a joint. So we just construct the joint in the same fashion. We know that the joint runs along the z-axis. We know that the links run along an x-axis. So we can actually build that up quite simply. Remember, of course, we've got two different types. We have the displacement or prismatic joint, or displacement which is d, and is variable in the prismatic joint. An angle of theta, which is variable in the revolute joint. So, to describe a joint, you have effectively got one more variable, and that will come in a second. In any joint, you can only have one variable. So it's either going to be rotary or prismatic. It's either d or theta. You cannot have both d and theta being a variable. So when you come to do exercises in this, if you've got a joint which comes out with two variables, you have done something wrong. It's as simple as that. So here we are with our link down the bottom, running on the x-axis. So our joint is going to run along the z-axis. And that will give us that new frame. So all we're doing effectively with all the kinematics, to put it very simplistically and very bluntly, all we're doing is moving a simple frame around the structure and ensuring that that frame satisfies certain rules. Like the frame moves along an x-axis into link, that frame will move round a z-axis if it is a joint. So there's only one further thing we've got to describe. Not that, but that. So D is the distance between this link here and that link there. So we've now got a whole set of what we call geometric parameters. I have got enough information in those four parameters to describe a full robotic system. So, what we do, we're not going to do today, we'll do it whenever, Thursday, wherever, looking at timetables. So, I'm going to take the system collection of joint links. We put those together as a joint link pair, because that makes life more difficult. So, when you go through and analyze a robot, we have to, or for a manipulated chain, we can start anywhere, finish anywhere, go any route we want. However, we have some little rules to make life a lot easier. We minimize the number of variables. That's by selecting the right start point and the right end point. Reflect the mechanical arrangement. So if the robot looks like a standard robot, we follow along that robot. So we map the robot into the kinematic world like that. And we also maintain the sense of direction. So if that robot joint is programmed and the designer of that robot says that will go from north 360 that way around, we map our joint to that direction. We don't have a joint pointing one way and the robot rotating another way. It just adds to confusion. So we minimize the number of variables, reflect the mechanical arrangement, and maintain the sense of resolution and direction resolution. So we don't have this problem of going from theta to 360 minus theta. So that is as far as that. So what I want to do, I won't do it this afternoon, do it next time. We take this robot, and it's got 5 joints. It's a paint spring. 5 joints, therefore it will have 5 joint link pairs. Alright? So the simple thing we've got to do is decide what those values are. And you'll note that all you are given is S1, S2, S3 and S4, which are the lengths of the segment between each of the joints. And you've got joint 1 through to joint 5. 5 joints, 5 joint link pairs. So there must be something around there which has 0 in it. So what I will do next time, we will sit down with this and we'll spend a good 20 odd minutes just going through this particular example. If you can grab that example, this first example, you should have no problems with anything else because this is the core kinematics. So I'll stop there, we'll leave it there and we'll pick that up on Thursday.
Saya berapa? First. Ready?